Okay. Hello, everyone. My name is Runzhou Han. I'm a fifth-year PhD student at Iowa State University. Today, I will be presenting our work, PROV-IO Plus, which is a provenance framework for scientific data on HPC systems. This work is a collaborative work from Iowa State, the Ohio State, Lawrence Berkeley National Lab, UNCC, and Samsung. Okay, let's start with the motivation. The very first motivation is the scientists want to know their workflows better. In this figure, I'm showing a typical workflow running on supercomputer. And we can see between the input data and output data, there can be multiple tasks running parallel, multiple threads, and there can be multiple intermediate data states. And I'm using this figure to show the complexity of a typical HPC workflow. And the fact is, the workflow users typically don't have enough observability on their workflows during the execution. So they want to know their workflows better. For example, scientists may want to know what slows down their workflow, like which tasks the workflow is bottlenecked, or which hyperparameter has been used and has the best training accuracy. However, due to the increasing complexity of HPC systems, it's not straightforward for them to get those information or either to observe what exactly happened to their workflows. So data provenance is an effective way to improve observability. Data provenance describes the life cycle of an data object, including all the intermediate state and all the I/O operations has been applied to it. Provenance framework is developed to track and manage data provenance. In a provenance framework, the provenance is described as directed graphs. Existing provenance frameworks include PATH and PATH-v2, which are developed for in-kernel provenance, and for user space provenance, there are Komodo and ProLake for user space workflows. So all of those existing works have some limitations when we want to use them in HPC systems on HPC workflows. The first thing is the granularity. Most of the existing works typically only covers file level information of workflow data, like I show in this figure. Unfortunately, scientific data formats such as HDF5 has nested inner hierarchy and is self-described. So when we look into it, it's like a directory rather than a file. So there can be concepts like group and datasets inside a single HDF5 file. But those fine-grained HDF5 data concepts and I/O concepts cannot be captured by existing efforts. But in HPC workflows, this information is extremely important because those applications are directly built on HDF5 APIs. The second limitation is compatibility and portability. Since existing works are typically not developed for HPC environment, substantial porting effort is usually needed if we want to use them on HPC workflows. Here I'm showing part of the dependencies of existing work, Komodo. And we can see if we want to run it on HPC system, we will have to port a lot of non-basic third-party dependencies. The third limitation is transparency. Existing works such as ProLake need scientists to insert provenance APIs into their workflows manually, which is not desirable. So these three limitations imply that a better provenance solution for scientific data and workflows on HPC systems is necessary. Then I will introduce how we develop our provenance solution. We first need to know what people want to know from provenance. We start with a survey on the real provenance needs of scientists. To this end, we discuss with 4 research groups from different domains, and they're from national lab and industry. The research domain includes physics or AI for science and I/O performance tuning. We learned that in top recall, which uses graph neural network to help quark reconstruction emulation. The users wants to have version control on their workflow metadata to reduce the graph neural network training time. And in DASA, which is an acoustic sensing workflow, the scientist wants to know the lineage of data products. And in another HPC bench-based synthetic workflow, users wants to know the I/O stats and performance bottleneck. And the last one is Maxtron LM, which is derived from Transformer, which is a large language model. The users want to keep the consistency of checkpoint configurations. So we summarize the people's provenance needs and into 4 basic information types that our provenance framework need to cover. They are data information, task information, configuration information, and relation information. As I mentioned earlier, provenance are managed and described as directed graphs. The graph has to follow some specifications, which we call them provenance model. We derived our PROV-IO plus model from W3C provenance data model PROV-DM. PROV-DM divides provenance information into 3 basic classes. As shown in this figure, they are entity, agent, and activity. PROV-DM provides a mapping between in-memory graph and on-disk RDF triples, which is a human-readable data format and can be queried like a database. In PROV-IO plus, data objects are classified as entity, I/O APIs are classified as activity, and callers of those I/O APIs, such as program or user information, are classified as agent. Since PROV-IO plus model is derived from PROV-DM, it's also interoperable with other PROV-DM compliant data models, such as PROV-ML and Komodo model. PROV-IO plus model is proposed as an I/O-centric model, so it covers most of the important data concepts and I/O operations in HDF5 library and POSIX syscall library. Besides low-level I/O information, PROV-IO plus further provides an extensible class for high-level workflow information, such as the type of the workflow. It can be like acoustic sensing or synthetic or machine learning, and also the time information. An extensible class can be extended flexibly with new concepts such as some machine learning concepts. After introducing the model, let's move to the framework design. Here is an overview of the PROV-IO plus framework. First, we can see that all the framework behaviors is guided by the model, the PROV-IO plus model. There are 3 major components in the framework: a tracking component, a provenance store component, and a user engine. The tracking component transparently tracks workflow provenance by letting I/O operations pass through and only captures provenance information. Specifically, HDF5 I/O is tracked with HDF5 provenance vol connector, which is part of the HDF5 vol framework, and we just insert PROV-IO plus APIs into the vol connector to track the provenance in graph format. And the tracker component currently supports major I/O operations from HDF5 library and POSIX syscall library. PROV-IO plus library also provides a Python interface for users to add concepts to extensible class and manually insert tracking APIs into their workflows. Next is the provenance store component. It maintains graphs of provenance records as RDF triples. To persist a massive amount of concurrent provenance efficiently, PROV-IO plus have each MPI rank writes to its own provenance file, and we consolidate all the provenance files together afterward. The user engine exposes a configuration interface for users to set provenance levels, basically specifying what information you want to track. It also provides query interface and visualization interface for users to analyze provenance. To support newer HPC systems, which only accepts containerized jobs such as Singularity, PROV-IO Plus is developed with a containerizer to wrap PROV-IO together with the target workflow into the container image. For more design details, please refer to our preprint paper released on arXiv. Now I will show how we evaluated PROV-IO Plus with real workflows and our results. We evaluated PROV-IO Plus with 4 workflows on Cori and the supercomputer at Samsung. On Cori, we used up to 64 nodes to measure PROV-IO Plus with top recall data and H5 bench-based synthetic workflow. And on Samsung supercomputer, we measured Metron LM with up to 8 100 GPUs. I'm listing the information we tracked for each workflow with PROV-IO Plus to meet the user's provenance needs, but due to time consideration, I will skip the details of them. Let's first have a look at tracking overhead. We observed the maximum tracking overhead in DASA workflow out of the 4 workflows. The figure shows the tracking overhead of DASA. In this figure, the x-axis is experimental scale, and y-axis is normalized completion time. We observed that at maximum 11% tracking overhead in DASA. And overall speaking, we found tracking overhead is less than 3% in more than 97% of all the experiments. Next is the storage overhead. So the storage overhead stands for the extra storage space consumed by RDF triples. In the 4 files, in the 4 figures, all the x-axis are still experimental scale, while all y-axis is our provenance size. So note that the 2 figures in the middle, B and C, their x-axis are in log scale, so it looks like not linear, but actually all of the 4 figures scales linearly with the scale. Yeah. We also compared PROV-IO Plus with PROV-Lake in both tracking and storage overhead on top recall. The left figure compares tracking overhead, while the right figure compares storage overhead. We observed PROV-IO Plus has less tracking overhead when there are more training epochs, which is more realistic in production. And PROV-IO Plus always has lower storage overhead than PROV-Lake. Finally, I will demonstrate how we make use of the provenance, basically how to visualize and query provenance to answer those questions from scientists. Here I'm using DASA for explanation. DASA users are interested in the backward lineage of their data product. For example, what's the origin file of the output data decimate.h5? From this figure, we can easily see the origin is on the left side, wetstack.tdms. However, if someone doesn't know how the workflow looks like internally, or he doesn't know the input or output paths of the workflow, he need to use provenance to get those information. So he can either visualize the subgraph or use Sparkle query to get the information he needs. The first way is to visualize a subgraph of a particular MPI rank and visualize the subgraph. So I'm showing in the figure below. And the second way is to just use Sparkle queries to get the predecessor information. And I'm showing the example queries on the right side. Note that this is a simplified figure because I omitted the detailed passes and the thread information just for demonstration. To make a conclusion, we identified scientists' real provenance needs, and we developed our provenance model and built a provenance framework called PROV-IO+. We evaluated our framework on 2 supercomputers with 4 workflows and showed the efficiency and effectiveness of our framework. In the future, we plan to develop better provenance post-processing methods, and we want to provide more user-friendly provenance query APIs. If you are interested in PROV-IO+, please check out our code on GitHub. And the Docker image is also available online. So this will end my presentation today. Thank you for listening. Happy to answer questions now.
Any questions? What was the provenance score that you are using?
We're just using RDF files. We're not using any database. It's just file, plain file.
Straight audio.
Yeah.
Okay.
But you can load those RDF into some graph database for further analysis.
Oh, there's a question. Yeah, speak up.
Well, I think that someone asked where the essentially this provenance information, which I think is RDF triples, where they stored. I couldn't hear.
I'm sorry, can you say again?
He was asking same question I asked.
Okay.
Where did you store the RDF triples? And were they in Turtle or XML or?
We're in Turtle.
Okay.
So it's actually configurable. I typically use Turtle, and I can also use XML. Yeah.
Yeah. So Alexander, did you hear the answer?
Yes. So the output goes to some text file or something else.
It's not text file. It's Turtle file. It's format.
Okay, yeah. Okay. Yeah. Okay. But that's text representation. But so after you have a run, and assuming you have a file with Turtle RDF, where does it go after that?
Where does the RDF go? Or
yes.
So one way is to load them into RDF the graph database, or we can just use some scripts to manually consolidate them. And we can, so the provenance provides the necessary information to answer those questions. And we will provide query APIs for the scientists to grab the information from the RDF graph. Does that answer your question?
Yes, thank you. And the final one, so do you ever envisage those HDFI files for which we have provenance kind of leaving the system that they were generated on? And then what would be required to ship those HDFI files with their provenance data? Have you thought about that? Or is that like a part of some kind of possibility?
He was asking whether you were considering sort of co-locating them, basically.
Oh, yeah.
When you send somebody an HDFI file, that the PROV information is available either through a DOI or any kind of packaging.
Yeah, so actually at the beginning, our thought is because HDF5 itself is self-describing, we're considering to put the provenance along with HDF5 inside HDF5. So the provenance co-locates with the data. But after some research and for some reason, we decided to separate them into different locations. And so basically, if we run it on the supercomputer, they're actually stored on the same parallel file system, and they're in the same system, but they're just in different locations. Yeah, that's my answer.
Okay.
Okay, thanks.